Recording.
Or-
Never mind.
Okay, sorry. Hi. So welcome to another edition of GOCC. Today we have Bailey Sarkovic from the University of Bonn. And today she'll be talking about the Matroid complex and its homology. Before we start, let's go over our community guidelines. We are all learning. Everyone has something to contribute, and no one has all the answers, including the speaker. And with that, let's ask Bailey to present her very good looking slides. Take it away.
Thank you so much. Thank you for hosting me and for the opportunity to speak. Today I want to talk a little bit about the Matroid complex and the associated homology. This work is joint with my collaborators, Benjamin Ashlock and Jacob Bocciarelli, and we worked under the wonderful mentorship of Juliette Bruce. Also, thanks to the Midwest Research Experience for Graduates, hosted by the University of Michigan. This was a really nice program and let us think about some really interesting questions in this area. Okay. So maybe before I get started, I want to give a little bit of background, maybe motivate some of our work. So it was in the 1990s that Savich introduced what's known as the graph complex. And the graph complex turns out to be really interesting. This was found in more recent years because its homology actually has a lot of topological applications. So for example, the homology groups of the graph complex encode certain homotopy theoretic problems. For certain classes of graphs, they govern rational homotopy type of knot spaces. These homology groups compute homology of moduli spaces of curves, and Savich remarks that they serve as a, quote, universal characteristic class for diffeomorphism groups of manifolds in odd dimensions. So needless to say, the graph complex is a really rich and interesting object, and this naturally motivates some interest in its Matroid analog. And so today, kind of a brief roadmap of what we'll be talking about. We'll start with Matroids, kind of a general overview and why they're interesting. We'll be building up the construction of the Matroid complex, talking a little bit about why it's interesting, going over some of the results that we showed and the many, many questions that are still open that we would like to understand. So first, what is a Matroid? So many of you probably worked or studied Matroids, but maybe not. Loosely speaking, a Matroid is a combinatorial object that abstracts various notions of independence appearing across many different areas of mathematics. So maybe before we explore some of their formal properties and their formal structure, I want to illustrate a little bit of their origin story because I think it's kind of nice. So it was in 1935 that Whitney published his On the Abstract Properties of Linear Dependence. And at the time, Whitney was working in graph theory, but in the same year, Takeo Nakasawa published his series of papers on the axiomatization of linear independence. And shortly after, sometime in the 1930s, van der Waerden also became interested in generalizing not only linear independence, but also algebraic independence. And so perhaps most impressively, this new kind of object was already garnering a lot of interest across several different areas of math. I think it was Birkhoff who also realized shortly after the release of Whitney's work that Matroids were secretly lurking in the background of his own work on semi-modular lattices. And so it's not so surprising that three very well-studied flavors of Matroids are the graphic Matroids that arise in graph theory, the linear Matroids arising from linear algebra. These are, as you might know, the collections of linearly independent vectors, and then also in field theory, and these appear as transcendent species of field extensions. So we'll go ahead and proceed to some definitions. So what is a Matroid? The data of a Matroid is a pair, where the first element in the pair is simply a finite set. We call this the ground set, and the second element of the pair is simply a collection of subsets of our ground set that satisfy two axioms. We call these subsets the bases of our Matroid. And the first axiom simply says that this collection is not empty, so we have to have at least one basis element. And the second axiom, this is known as the basis exchange property. This basically says that for any two distinct bases, B1 and B2, if we have some element in B1 but not B2, call this X, we are guaranteed some element Y in B2 but not B1, such that we can exchange Y for X, and this yields another distinct basis. And then we call a subset of our ground set independent if there exists some basis containing it. And so I might just remark here that there are many different characterizations of matroids. You can characterize them equivalently according to flats or circuits, which I'll introduce in a couple of slides. But we choose here to characterize them according to bases. So maybe we'll talk about a quick example. And we'll use a graph, the three wheel, which we know and love. And so we can generate its matroid simply by labeling all the edges of the graph, 1 through 6, and then this gives our ground set. And then our bases are simply given by the spanning trees. And we just recall that a spanning tree is a subgraph, which is a tree and which meets every vertex in the graph. And so I've listed them out here. But maybe if you prefer the linear algebra perspective, you can actually recover the same matroid simply by forming the incidence matrix associated to the graph, and then taking your linearly independent column vectors. And these maximal collections of linearly independent vectors will be your bases and will be associated to these spanning trees. Now, there are a couple of other really useful formulations of this second axiom. And perhaps on first glance, these look a lot more, these seem a lot stronger, but actually they're equivalent characterizations, and they're not trivial to prove. The first one was proved in 1969, and the second came shortly after. But the first one simply says, again, if we have two bases B1 and B2, and we have our element X in B1 but not B2, and our element Y in B2 but not B1, this Y, whose existence is guaranteed by B1, we could also exchange Y for X in B2, and this also yields another basis element. So this is the symmetric version of just the first formulation of B2. And then maybe in practice, even more useful is this B2 star star, and this is known as the multiple symmetric basis exchange property. This basically says we can do this not only for singletons X and Y, but in fact, we can do this for subsets as well. And so this will be useful for us in some results later.
I have a quick question about this multiple symmetric basis exchange property.
Sure.
Can I not always choose X and like X equal to B1 minus B2 and Y equal to B2 minus B1 kind of regardless of whether or not this is a matroid? Like if I just have a collection of sets?
So you're just choosing X, and then you're guaranteed the existence
Got
of
it. Okay. X is something I pick, and then Y exists. Got it. Wonderful.
Yes. Yep. You can make a special request for X, but then you don't exactly have control over what Y might be. And so, yeah. Yep. Okay, so one quick fact that follows from B2 by iterative application of B2 is the fact that all bases have the same cardinality. And as a result of this fact, we can introduce a rank function. So we can equip our matroid with a rank, and this rank is given by this now well-defined cardinality of all the basis elements. And then we can also extend this rank function to any subset of our ground set and just declare that our rank is given by the cardinality of the maximal independent set contained therein. And so it's not so hard to see that a subset of our ground set is independent if and only if it witnesses its own rank. Okay, so there are quite a few definitions on this slide, but don't worry, on the next slide we'll have a nice example illustrating what all these special kinds of elements are. So there's some special kinds of elements of our ground set as well as special subsets. And the first is a loop. So we call an element of our ground set a loop if it appears in no basis. And so, for example, maybe jumping back to linear algebra for the moment, the zero vector would be an example of a loop because the zero vector appears in no basis in some finite dimensional vector space. And then dually, so the dual notion to that is what we call a co-loop. And an element of our ground set is a co-loop if it appears in every single basis. We also have circuits of our matroid. So a circuit is simply a minimally dependent set of our ground set. And in particular, we call two elements x and y parallel if they appear as a circuit. And then finally, a subset of our ground set is called a flat if this subset is, quote, closed under adding other ground set elements which do not increase the rank. So in other words, adding any other element of our ground set to F would strictly increase the rank. And just a quick fact that'll be useful later, parallel elements appear in all flats together. This is to say that given any flat, if x and y are parallel, x is an element of f if and only if y is an element of f. And if this weren't the case, then f would be a genuine flat because we could always add the other one that doesn't appear without increasing the rank. So here's a nice example. This is nice and visual since it's a graphic matroid. So for instance, a loop is given by exactly what your intuition would expect, just some loop in the graph. And this is indeed a loop because, again, kind of in the setting of graph theory, no spanning tree will contain a loop. And then we also have our edge A. This is a co-loop. And this is because this vertex in the lower left corner is only accessible via the edge A. And so every spanning tree will include this edge. And then we have parallel elements I and J. And it's easy to see these are parallel because removing either I or J from the pair will induce a tree or an independent set. And then finally, this triangle KML, this is both a flat and a circuit. It's a circuit in the sense that if you remove any edge, KM or L, you induce a tree. And it's a flat in the sense that if you add any other edge in the graph to this set, you can now fit a tree of strictly larger cardinality into that subset now, into that subgraph. Okay, so
Small question. So in a flat, okay, so you already have all the parallel elements, right? So you can't add a new parallel element.
that's right.
Okay, so if I were to like take the triangle, add an edge on the side, that would be parallel. And so it would already be included in my flat. Okay, sorry, got it.
No worries. Yeah, that's right. So of course there is a category of matroids. And in the category of matroids, our morphisms are given by strong maps. And strong maps are just maps on the ground set such that the pre-image, if you take any basis in the codomain, its pre-image is a basis in the domain. And so this allows us to ask whether or not two matroids are isomorphic. And they're isomorphic if there in fact exists a bijection on their ground sets, such that some subset is a basis in M1, if and only if its image is a basis in M2. And then also we have, this is a special kind of matroid. I'll just introduce this now. It'll become useful later. But we have what's known as the Rangar uniform matroid. And you might already guess what this is. It's the matroid on n ground set elements such that every possible subset of size R appears as a basis. Okay, so I think we have all the tools now to construct the matroid complex, the analog to Koncevich's graph complex. And to do so, we're going to first recall the recipe for a chain complex. So if we remember, we have a family of vector spaces over some field F, and we have a family of F linear maps or differentials, which compose to 0. And of course, our nth homology is given by the kernel of our nth differential modulo the image of our n plus first differential. And so essentially now we need a family of vector spaces for our matroid complex, and B, some differential maps. And so we'll start by defining our vector spaces. So we're going to be working over the rationals, so this will all be over Q. And we'll start with the space generated by all pairs. And these pairs are pairs of a matroid M and an orientation pi on our ground set. This orientation is a total ordering up to even permutation. So in other words, we only have positive or negative orientations. And we view it in this way by letting pi be just a wedge. And then our rational matroid complex is given by the family of vector spaces, where each vector space is generated by these pairs M pi, except we identify a pair with its negative under the negative orientation. And we also identify isomorphic matroids. We identify the pairs consisting of isomorphic matroids, and where the orientation of the latter is simply the orientation induced by the isomorphism. So because these matroids are now equipped with orientation, this isomorphism can sort of track how the basis or how the ground set elements are permuted.
Just a quick question. The N here, is that, where is the N showing up in this definition? Number of elements in the ground set?
Yes.
Okay, great.
Yep. Okay, so I'll remark that there are a few different ways, a few different avenues to take to go about getting to this final vector space. And this was just one of them. There are a couple of other ways. So one in particular would be to take pairs where we don't identify orderings up to even permutation. We could just take all possible orderings, and then our space is larger and we can mod out by like a larger space. But yeah, so there are a couple different ways, but we ultimately get to the same final vector space. And this vector space is over Q, and it admits the basis consisting of isomorphism classes of matroids on n ground set elements that admit no odd automorphisms. And why is this the case? Well, if we had some matroid admitting an odd automorphism, then we could invoke our relations and actually deduce that this matroid class is just 0 in our complex. And so you have this, this short computation here at the bottom.
We have a question in
Bailey,
the chat.
Oh, yeah.
So on the previous slide,
Okay.
yeah, what are the EIs here?
Oh, sorry. These are the ground set elements. Yeah, so I'm just labeling our ground set E1 through EN.
Okay, so yeah, you've chosen, you know, for each of the N element, for each N, there's a ground set of N elements, and they're just E1 through EN.
Yeah, yeah.
Wonderful.
Sorry for that confusion. Yeah, I think, yeah, E, I maybe used E, or was inspired to use E by the edges.
Awesome.
Edges and graphs, but yeah, sorry. These are just ground set elements. Okay. Okay, so we're almost there. In our recipe, we needed 2 things, but we still need our last thing, which are our differential maps in our chain complex. And so maybe before I give definitions, we might think about what we would want these to be if we were to sort of reconstruct everything on our own. And so for this, maybe we'll jump back to the setting of graphs and recall that we actually have 2 nice graph operations given by deletion and contraction. And in fact, deletion and contraction are the 2 operations that Kinsevich uses in his graph complex. So maybe we'll see if we can build something analogous for matroids. And so in the case of deletion, if we have our graph W3 again, our 3-wheel, and we delete edge 1, then what happens maybe at the level of the matroid? Well, our ground set has just gone down by 1 element. So our new ground set is given on elements 2 through 6. And then what happened to our bases? Well, now that one of our edges is gone, we only keep as our bases the spanning trees that didn't contain one, that didn't intersect the edge one. And similarly, in the case of contraction, what happens here, if we contract our edge one, we've now collapsed it down to a vertex. And so again, our ground set goes down by 1. Our new ground set is again now given on elements 2 through 6. And what would we want for our new basis elements? Well, our old basis elements were just all the spanning trees of our graph. But now we've collapsed an edge down to a vertex. And we know that spanning trees meet all vertices in the graph. So in some sense, all of our new basis elements should be those spanning trees that absolutely contained that edge 1 in the first place. Except we now remove the 1. So maybe as our bases, we'll take all of our old bases that intersected 1, except now this 1 here that I have in red in all of these places, this is actually just a ghost. We don't keep the 1 because it's not in our ground set. So our new basis elements would all have cardinality 2. These would just be pairs. And so indeed, this is how we define our differentials for matroids. So in the case of deletion, formally, we say that M delete some subset of the ground set S is simply the matroid on the ground set E minus S, whose bases do not intersect S. So we just take a subset of our old bases. And then to define contraction, it's actually a little bit easier to maybe first introduce what's known as the dual of a matroid. So we define the dual of some matroid M as the matroid M star given on the same ground set, but whose bases are just the complements of the bases of M. And so now contraction, formally defined, is simply the matroid given by passing to the dual, deleting S, and then redualizing. And it's sort of like a fun, maybe exercise to think about why this is true and why this makes sense in light of the example for the 3-wheel. But this is a nice way, a nice concise way of defining contraction in terms of deletion.
Wait, what's the dual again?
The dual?
Yeah.
Yeah, so the dual of some matroid M is just M star, which is given on the same ground set, except now we take complements of all our bases. So your bases are just subsets of the ground set, and then you just take E minus all of those bases.
Yeah, but so for like a graph, if you have a tree and you take a complement, that won't be a tree anymore, right?
Yeah, that's right.
And okay.
So in the perspective of like the original, these are not, these won't be spanning trees, but in some dual sense.
Yeah. Emmy is asking, is it obvious that makes a legit matroid? Which up?
Yeah, so is it obvious? I guess no, but you can check that this definition meets the 2 axioms. So for example, if so maybe I won't go through the details, but you have B1 and B2, and you know that your basis is non-empty for M, and you also know you have basis exchange. You could, I guess, just check that M star, that B star, I guess, satisfies these axioms as well.
Sorry, Bailey, I have one other question on the previous slide.
Okay.
So looking at this, the contraction you're saying is, we can find the contraction, just, I guess I'm going to try saying it out loud and hope it's right. So we're taking the dual matroid, we are deleting, we're deleting the element S, and then we're taking the dual of that to get that. Awesome. Okay, great. Thank you.
Yeah, so as we were thinking about in the previous example, when you're contracting that edge and then you're asking for all the spanning trees that contained the contracted edge, but now you're removing the contracted edge, this kind of idea is conveyed in the idea of dualizing, deleting, and then dualizing again. Yeah, it's maybe not so obvious, but you can think about how taking complements and then deleting from the complements and then retaking complements is actually the same thing as we were doing previously. Okay, just one quick technical note. So we now have our deletion differential, and we're going to use this deletion differential in our chain complex. But one first note is that by working with the deletion differential, we're not actually making a choice, because as we saw, deletion is somehow equivalent to contraction in the dual, and so we can always just dualize, and we don't lose any information. So we'll be working from here on out with the deletion, but we're not like losing information in that way. So it's not actually a choice. And then also, so our deletion differential is given in this way here at the bottom of the slide, where this right-hand side is a formal sum over isomorphism classes, and we're summing over all possible deletions. So we're summing over the deletions of M minus some ground set element, but we don't sum over the ground set elements which are co-loops. And this is because if we were to delete a co-loop, our new basis would be empty. And this is because a co-loop existed in every basis in the first place. And so if we delete it, the bases we're left over with are non-existent. We have nothing. And this violates axiom B1. And so our sum will only be taken over our ground set elements, which are non-co-loops. And this is just, yeah, for legal reasons. And then, of course, for a chain complex, you have to check that this deletion differential squares to 0. And this is basically just, yeah, some technical argument. If you delete by ground set element EI and then by EJ, then the formal sum, the sum of sums you obtain at the end, just consists of pairs of terms and their negatives. And this is because if you delete by EI and then you delete by EJ, well, there's this index shift that's going on if I were less than J. And so you pick up one less negative than you would if you deleted by EJ and then EI. And so this first term here is just the negative of the second term. And so everything cancels. And so the square of the differential is indeed 0. And then also deleting by only non-co-loops is rank preserving. And this is because for any element of your ground set, which is a non-co-loop, you're guaranteed some basis which does not see X. And this basis will survive deletion by X. And thus, it'll witness the rank of the matroid after deletion as equal to the rank of the matroid before deletion. And so deletion by non-co-loops will preserve the rank. And so we finally obtain the matroid complex. And it's interesting to note that you can actually decompose each of these vector spaces, Cn, into a direct sum of fixed rank vector spaces, Crn. And this means that our matroid complex actually decomposes into fixed rank subcomplexes. And so somehow this makes it nice because we can understand our whole matroid complex in terms of these smaller pieces. So we can sort of tackle one piece at a time. And then by matroid duality, so I don't have any details here, but you obtain an isomorphism of chain complexes via duality, where deletion in this upper chain complex can sort of be mapped down to contraction in sort of the dual chain complex. And so this is really nice, and all these squares commute. And so, as I said, working with the deletion is not making a choice in any way. We're not losing anything because it's basically, yeah, basically the same as contracting in the dual. Okay, so maybe we'll move on to some results. And one first result is not so hard to see. So if you have a matroid M and it's a simple matroid of rank 2, so what does simple mean? It means that you have no loops and you have no parallel elements. So basically you don't see circuits until you consider subsets of the ground set of cardinality at least 3. And so if you have some simple matroid M of rank 2, then M is isomorphic to the uniform matroid on n ground set elements of rank 2. And why is this the case? Well, each pair must be independent, otherwise you would induce parallel elements or a loop. Either X or Y would be a loop. Another fact that will be useful later in kind of understanding the different pieces of our complex is this lemma here. So if we have some matroid, and if we have some parallel elements, A and B, of our ground set, then for any basis BA containing A and any basis BB containing B, and just as a side note, these must exist, since, right, so we have, yeah, so these are parallel, and so if it's the case that we can find, sorry, it's not, okay, yeah, so if it's the case that you can find BA and BB, then it happens that you can swap out B for A and BA and A for B and BB, and you also get these as your bases. And maybe just to see what's going on here. So you have your parallel elements A and B, and you somehow want to be clever, and you want to choose, we want to be able to invoke our second formulation of B2. So somehow it feels like our multiple symmetric basis exchange is what we want to use here. And indeed we can, by choosing as our first subset, basically everything possible. So we choose the biggest possible subset of BA that we can, that we can swap out. And this will guarantee that our Y that we can swap in is in fact what we want. It's all of BB minus the intersection and also minus B, such that we obtain the two bases that we wanted simply because if we didn't, there would be a contradiction in the rank. So this would contradict fact 1.1, which says that all bases have the same cardinality. And so this is useful for us. And we should also note that, again, these basis exchange axioms never necessarily let you choose both your X and your Y. You can choose X, you can make a special request for X, but you're only guaranteed the existence of some Y. And so that's why this result doesn't necessarily follow immediately, because we're actually demanding a particular X and a particular Y. Another result is that, so here at the lower tail of our chain complex, it happens that our vector spaces are usually 0. We have two edge cases. So when R is 1, when we're considering rank 1 matroids, there are two examples here. So in C11, in the case that M is just consists of a ground set of a singleton, and our basis is exactly that singleton, then of course it admits no odd automorphisms. And then similarly in C12, if your ground set was just a pair of elements and your basis was a single element, just one of them and not the other, then you also admit no odd automorphisms, because swapping the two would always disturb your bases. And so, but in every other case, when R is not equal to 1, we have that these two vector spaces are just 0. And this is just an argument by, you can take a couple of cases. So in the case that the intersection of all your bases contains at least 2 elements, of course, you can swap these two, and then you don't disturb your system of bases. And otherwise, you're guaranteed 2 elements not in the intersection, such that you can also swap them via an odd automorphism. Yeah, and this is special to these two cases, CRR plus 1 and CRR, because our bases are so large that we can make these kinds of arguments. Another result is that CRR plus 2 is actually also 0. So after checking some of these smaller cases, what you can do is you can here, it's helpful to pass the dual, because in the dual, our matroids are rank 2 instead of rank R. And somehow, in practice, it's easier to work with matroids of smaller rank than of larger rank. So we pass to the dual, and we make a similar argument. Basically, if you can assume, so it follows that your matroid contains at most one loop as a first step. Otherwise, if it contained more, you can always permute your loops, and this would be an odd automorphism. So after deleting your loop, if you further assume it's not uniform, uniform matroids always vanish, then it must be the case that your dual minus your loop contains parallel elements. And then the moment you have parallel elements, by our previous fact, you can permute these two, which is an odd automorphism, and thus your matroid class is just 0. And then you lift up, so you undualize, and it follows that CRR plus 2 is also just 0. And so with all of these vanishing results, you might wonder which families of matroids are non-zero in the complex. It seems like there are so many things that are 0. And maybe even more interesting, which families of matroids are non-zero in homology. And so maybe kind of jumping back to the setting of the graph complex, there was this strong interest in odd wheels, because it turns out that odd wheels were non-zero in homology in the graph complex. And so perhaps they're also non-zero in homology in the matroid complex. And this is something we investigate and we'll show in a couple of slides. But moreover, it turns out that the homology of the graph complex actually gives a lot of information about the top weight cohomology of moduli spaces of curves of genus G, as well as the reduced homology of the moduli space of tropical curves of genus G in volume 1. And so the natural question is, can we get similar homological information out of the matroid complex? And it's postulated that perhaps the homology of the matroid complex witnesses the top weight cohomology of not the moduli space of algebraic curves, but the moduli space of principally polarized abelian varieties. And so this is one possibility that would be really interesting. But for us, we decided to actually try and investigate these wheels as one source of non-zero data. And so it turns out that the wheels don't vanish in the matroid complex, but they actually do vanish in homology. And this is because, so first, if you hit the class of the odd wheels with the deletion differential, it turns out it's in the kernel, because I won't give the details here, but you can always find two edges that you could swap. This would be an odd permutation, which does not disturb the bases, and thus means that that the odd wheel vanishes after deletion. And then it also happens that the wheel is in the image of the deletion differential, because you could just take your odd wheel and you could adjoin a loop. And then because the wheel is in the kernel, it happens that if you delete any ground set element that's not that loop, you get 0. But the moment you delete the loop, since our sum is taken over all possible deletions, you just get back the wheel. And so, and so ultimately our wheel class here is 0 in homology in the matroid complex. But maybe I just want to remark here, this is, philosophically, this is sort of interesting, because I guess as you pass to coarser abstract spaces, for example, when you're considering abstracter objects like matroids as opposed to graphs, you should expect in some sense to lose some information, to lose some refinement and some precision. The reason that this happens is because graph automorphisms are harder to come by than Matroid automorphisms. And so the automorphisms we were able to invoke here and perform here to show that the wheel class is 0 in homology were not graph automorphisms, because the restrictions to being a graph automorphism are much higher. Since graphs have this greater inherent structure, as opposed to Matroids. Matroids don't see the connectivity of the underlying graph. And so it makes sense that we sort of lose a little bit of information and that more things will vanish in the Matroid complex than in the graph complex.
We have a question in the chat and then also a question from me, but I'll start with the question in the chat. So it says, to talk about 0 in homology, do we need the Matroid class to be the kernel in the first place? Or the kernel in the first place, sorry.
To be in the kernel.
Yeah.
Yes. Yes.
Wonderful. I had my own question.
Okay.
Whenever we are talking about these odd wheel graphs, are we talking about these graphs like as some, whenever we're talking about the Matroid associated to them, are we talking about the graphic Matroid associated to that graph, or are we talking about considering this graph as a simplicial complex?
That's a good point to clarify. We're considering the graphic Matroid associated to this graph.
If that's the case, I thought graphic Matroids couldn't see isolated vertices. Like, I thought our ground set were edges. And so if you add an isolated vertex, that wouldn't add a loop because there's no edge.
Yeah. Yeah, this is a little bit, I have that written on the slide. This is a little bit imprecise. Yeah, okay, I guess maybe this should just ignore the part about the isolated vertex. This is just a loop. Yeah, so maybe this dot is very misleading. This is a loop in the sense of the definition I introduced many slides ago.
Okay, so we added a loop somewhere on the graph. Doesn't really matter because it's a Matroid, and so it's just a loop. Exactly.
Right. Okay. Yeah, sorry about that. Yeah, that's not correct. But yeah, you're right. So at the level of Matroids, we just have this abstract loop, and in the graph, this would just be some loop somewhere. Yeah. Okay, so we also have some computations. We were using Macaulay 2 to actually compute sort of this parts of this Matroid complex in these higher degrees. And with that, we were able to find that homology actually is 0. So there's no homology for all n less than or equal to 8. And we also have this lower tail of the Matroid complex classified, and it's given here. So we have these direct sums. As I mentioned earlier, you can decompose the complex into a direct sum of rank R subcomplexes, and so we were able to compute these rank R subcomplexes, and we have those results here. And yeah, maybe I should say Macaulay 2 is really nice, but it only stores Matroids on ground set size less than or equal to 9. And so we weren't able to, if you see in this table here, there are 2 entries we couldn't fill in yet just using our Macaulay 2 algorithm because we didn't have access to all Matroids on larger ground set sizes. But otherwise, yeah, these were our computations. And roughly what we did with the algorithm is we just imported these, basically all of these Matroids on these small ground sets, and we filtered these lists by checking for the admittance of odd automorphisms. And this allowed us to fix ordered bases. And then for each basis element, apply deletion to generate a column vector, its resultant column vector in the next, after deletion. And this allowed us to build up our deletion differential as a matrix, and then have Macaulay 2 compute homology of the linear map. And so what would we still like to understand? Well, first, I didn't talk too much about this, but it happens that our graph complex is actually a differential graded Lie algebra. You have a Lie bracket, and you get a Lie bracket via a non-commutative binary operation, which is essentially just graph insertion in the setting of graphs. So a natural question is if we can equip our Matroid complex with something similar, with a compatible graded Lie bracket, to transform the Matroid complex also into a differential graded Lie algebra. And sort of the first difficulty in doing so is the fact, as I mentioned before, Matroids don't see connectivity. And so we don't really have a notion of insertion. In the graph case, we were able to actually insert graphs into the neighborhood of a vertex. But we don't have these notions of neighborhood or adjacency or connectivity at the level of Matroids. And so it's sort of unclear and not so well defined what we would want maybe an analogous Lie bracket to be, or a binary operation. But that's an interesting question nonetheless. Of course, we're also still hunting for homology in higher degrees. So as I mentioned, Macaulay 2 only stores Matroids. By degree, I mean the cardinality of the ground set. So it's only classified all Matroids on ground set sizes up to 9. And so that makes it difficult to compute homology in Macaulay 2 for larger Matroids. But perhaps something else another place to hunt for homology might be in other subcomplexes, subchain complexes, and perhaps one natural choice would be the regular Matroids. And regular Matroids are just those Matroids realizable as systems of vector spaces over any field, systems of vectors over any field F. And there's a nice way, I think, to work with these Matroids. You can, there's like the Revlex ordering, and and there are some databases which do have these stored, and so maybe if we can work with this Revlex, we can possibly find homology in that subcomplex. Are there any questions?
Let's thank the speaker. That was wonderful, Bailey. And yes, and as Bailey said, are there any questions? I'll just read the one out in the chat. Are there any reasons to use cube as coefficients? Why are we using rationals?
Yeah, I think for us, we use the rationals because the rationals are used in the graph complex. So this was maybe a natural choice for us, but other than that, I don't immediately think of any particular reason.
Is the Matroid complex realizable as the chain complex of any CW complex?
Oh. I am not so sure off the top of my head. This is a good question. Yeah, I don't know. I'd have to think about it. Sorry for no answer.
And, it's our third guideline. Nobody has all the answers. And
Good
what
question.
happens if you go to positive characteristic?
Sorry?
If your base field is of positive characteristic, what happens? If you were to go to like a finite field instead of cube.
Okay. I don't know. We haven't looked into that. We haven't thought about that. I don't know if that's done in the graph setting either. Yeah, what would you expect though? Yeah, I'm not sure. That'd be really interesting. You would expect more vanishing, I guess, but yeah, we haven't thought about this, so I'm not sure.
Hopefully the construction isn't too loud, but I had a question about, do you have any reason to suspect homology does or doesn't exist for higher values of n in this complex?
Yeah, that is a great question. I really don't know, because like one first promising source was the odd wheel class. But then it turned out that those were actually vanished in homology. And so I'm not so sure. I think that if there were to be homology, yeah, we would have to look to non-graphic matroids. Because sort of the best candidate of graphic matroid turned out to vanish. Yeah, so looking to these regular matroids or these other families of matroids is, I think, maybe the only hope. Yeah.
There's another question. Is the graph complex of the graph G the matroid complex of the graphic matroid of G?
Is the graph complex of the graph G
The matroid complex of the graphic matroid of G.
No. This is right. So they're not the same, because our vector spaces are different. So in the graph complex, we have basically our basis in every vector space is just generated by isomorphism classes of graphs, but this is not the same as the isomorphism classes of their matroids.
So just to make sure I'm understanding this correctly, like there isn't really a graph complex of a graph G, like there is the graph complex, and G can be an element of that might not be zero.
That's right. Yes. Yeah. So there is no graph complex of associated to a single graph. We build the graph complex, and then these graphs, these classes of graphs are elements. Yeah, you can have like subcomplexes generated by or associated to certain families of graphs, but you don't have, there's no complex associated to just a single graph G.
Another question.
So it's different in that it makes sense to talk about the matroid complex of a matroid.
No, so
Okay.
Yeah.
So you've studied the matroid complex, which whose the vector space elements are equivalence classes of matroids.
Yes.
And the graph complex is a complex whose vector space elements are either graphs or equivalence classes of graphs.
Yes, equivalence classes of graphs.
Okay,
yes,
so then
right.
the guess my question would then be if the matroid complex is restricted to graphic matroids, does it become isomorphic to the graph complex? In other words, I'm asking, is the matroid complex actually a generalization of the graph complex?
So one immediate concern I have is that I don't think you could necessarily form the subcomplex at the level of matroids, just associated to graphic matroids.
Okay.
You would need to ensure that it's closed, that these operations, because most matroids are not graphic matroids, and so you would need to. I don't think there is a subcomplex just associated to the graphic matroids.
Oh, so in the Matroid complex, we need to have a certain closure.
Yeah.
On an operation on a Matroid that results in a Matroid.
Yeah. So that's why these subcomplexes, like, you have to be a little bit careful. You have like the rank R subcomplex, and you have the subcomplex for regular matroids, but it's not the case that you can just take any subcomplex you want. It would still need to be closed.
So what is the operation on the Matroid that plays the role there?
In the Matroid complex?
Yeah.
So maybe I'll go back. We have our notions of Matroid deletion and contraction.
Yeah.
I don't know if this is what you're asking, maybe.
Okay. So the operation under which you have closure is deletion and contraction.
Yes.
Okay, so the graphic matroids, class of graphic matroids is closed under deletion and contraction, certainly.
Okay, yeah.
And they correspond to graphic deletion and contraction, shrinking an edge and deleting an edge.
Yeah, I suppose. Yeah, yep.
Okay. Cool, thanks.
Yeah.
I'm wondering if I see the Kontesevich motivation for graph complexes was physics. Could you elaborate on that if possible? What the origin of his work was?
Oh, that's a good question. I'm not so familiar with maybe like the physics motivation of his work. I know he was working in like non-commutative spaces.
Okay.
And a lot of this came from some interesting results related to Lie algebras. And
okay.
Yeah, but I really don't know so much about this.
Okay, thanks. Okay.
Yeah.
Cool. Interesting subject.
We have a couple more questions in the chat. I think the original context for Yu Chan's question has been lost, so I will ask it, but I may ask for some clarification, which is, if we focus on 3 connected graphs, would they be the same? I'm not sure the same as what. But we also had a question from Emmy. Not that I know anything about graph complexes, but is there any relation between the homology of those 2 complexes, presumably Matroid and graph complexes?
Yeah, this is an interesting question. So at least sort of given what we've classified so far, no, because we only have zeros right now. I mean, I think this relates to another interesting question that we have as well, which is like, to what extent can you import sort of these results at the level of graphs into the Matroid complex? Yeah, as we saw, you could have 2 classes of graphs in the graph complex that are distinct, but that then both vanish in the Matroid complex, or that are the same, that have the same class at the level of matroids. So it's not so clear if there is a relation and what that might be. Yeah, it's sort of hard. It's sort of hard to say right now. If we could get our hands on some non-zero homology, then maybe we could understand that a bit better or have some direction. But
I actually did have kind of a follow-up to that response, because when Seth was asking whether or not the graphic Matroid subcomplex of the complex was isomorphic to the graphic complex, like, don't your results on odd wheel graphs already kind of rule that out because your homology filler, as
yeah.
I think of them, were also
yeah.
perfect Matroids. And so, like, if they were subcomplex, then those would still have homology.
Yeah, you're absolutely right. Yeah. Um,
Okay, I think,
Okay.
yeah, we seem to have had lots and lots of questions, but there's a temporary break and we are at the hour. So I think we should thank Bailey again.
Yes. Yeah. No problem.